Okay, we are back to continue, okay, our content from the last script, okay. Uh, Last time we talking about how to solve the FFT under the Matlab environment over here, okay. We already installed this Matlab environment and we implement actually from the sub drive here and FFT the drive contain a lot of Matlab code, okay, that has been designed along around this idea of this FFT extension Radix-r, okay, and we all have already seen that from the classical Radix tool, okay, the extension for general Radix-r, like for you consider r equal to 3, okay, this is a general formula, and r is equal to 4. We also implement r equal to 3, okay, Radix-r on under the Excel example for you, okay, and already gave you a homework to work on the Excel environment, okay. And the nice thing about the Matlab is that you are capable of solving this problem in a really large scale, okay, data by using a very easy command, right, or one object of FFT, okay. But today we will talk about the situation that under the Matlab application facing the same problem that you found under when you're using Excel platform. That at one point your software going to reach your limitation, okay. That limitation going to cause you that you not be able to solve that problem in real time anymore, okay. It means that there's some unresponsive. That's what they last time you saw in the clips, and or maybe I used the words uncomfort zone of the software reaching the level when your data become too large, okay, to be handled by their own RAMs, okay, the memory, the main memory, okay. And let's go back to this file we call the million point FFT, okay. This one, you might remember last time we created this program, okay, but it's a little, this one today is a different computer, so different function generation here. And you can see that this one is n is equal to still the same to 2000 million, okay, well, this one, and if I try to solve it, okay, if I try to run it, okay, still they're gonna say this, okay. Last time we already seen this. This is a new computer, not the computer from the last script, still responds the same. This means that the regular main memory installed on this computer, board of this computer that I use to give you a lecture here is they're reaching an uncomfort situation that the software didn't prepare to facing this type of problem, okay. And there's one thing that you have to go back and test your computer. Your computer have a very large amount, much larger amount of main memory, and even you install the GPU, okay, that normally you know when you play game on computer that this limitation may be a little bit larger than what I test here, okay. But over here I say that 2000 million reaching the limitation, okay. Today we will continue that. Suppose we are facing this type of problem, how are we going to solve, how are we going to find the FFT? Because now to input the data, the program didn't pass, so didn't have any chance to try this, okay. And the way that we can handle this, as you might recall, the methodology that we use when we're using the Excel environment is that we go back to the classical idea of Radix-r, okay. And from last time, as you know that Radix-r also can be represented in terms of this butterfly diagram, okay. And actually you can decompose the butterfly, a very large group of data here, may be separate into 8 pieces, okay, x sub 0 to x sub 7. This is for the time domain. Each of these can be a subvector or with a smaller size, and then you can keep performing using the operation indicated in the butterfly diagram. You're going to reach out here. So that's one way to do it, okay? That's one way to do it. But the simple way before using that butterfly diagram is to go back to the original formula of Radix-r and Radix-4. You can apply Radix-r. Radix-r, what does this mean? This means that if we be able to decompose this to R pieces, okay, therefore, okay, you can solving each decomposed part, okay, independent of each other, or in computing sense we call the parallel, okay, approach, okay. Suppose each of these summation, okay, you can solve it independent for other computers, okay, and then you can take all the results back here, okay, and substitute based on this formula of Radix-r, okay. Suppose you separate to R unit, okay, so there's going to be summation, the smaller fast Fourier transform. Suppose that once you make a decompose here, the size of problem reduced down to a manageable size. Manageable size means that it's not facing this command, not facing this situation. Okay, it can solve within a real time. Okay, so if you can do it here, okay, so you can solve each of these independent of each other, okay, and then take the result to put it back to get each x bar of k, where k is separated to n divided by r part, okay, and that's not exactly the bad idea, okay, but again, this is just one step of decomposition. Okay, and you know that from Radix-2, okay, in case of Radix-2 case, this one, okay, this means that once you decompose this, okay, you can get this results, okay, but to reach from here to here, if you apply in Radix butterfly diagram here, you can even reduce the computation. Instead of you have to instead of you just substitute directly only in this stage, okay, but our demonstration at this level, we're going to start with the simple and basic ideas that we apply just this Radix-r just one stage. Okay, this means that if I decompose this to R, and then I'm going to take the smaller FFT, that the FFT function object can be solved in real time, and take the results back and substituting for x bar k. Okay, but to apply the direct substitution here, you require R square, okay, computation, subcomputation. Why R square? Because for each k, okay, you need the results of R summation, the fast Fourier transform or subsystem of R, and then you need to add it all together, and multiplication for each step. So for each k you require R step of computation. Okay, but you have the number of k's that you can see that and you can see L, okay, for one, okay, for each k, okay, you can solve this, okay, not for each small k, for each L, okay, for each L value, okay, you can solve it by applying the R step of computation, because you have R subsystem, okay, and for all possible L, therefore you need to solve R square subsystem. But can we reduce R square here to R log 2 above? Yes, if you can do it, if you can understand. That's why I taught this one last time. The procedure that we're going to study next, okay, can be reduced by applying this butterfly diagram, okay. But that's not going to cover. You don't need to do it, but if you understand the concept, you can apply it, but I don't have any example for you to illustrate to you. Okay, so today we'll talk about Radix-r here, okay, and how can we code it in the Matlab environment, and how do they apply for the large scale problem. And you have to remember one thing, that for the first problem that we face here, okay, you're facing the problem that when you have such a large problem, you don't even have the main memory to handle it. Okay. So the very first step you need to do is that you need to write a program to keep process the input data, just only the subsystem. Okay, and then you have to make sure that you don't load all the data to work in the main memory at the same time. So now, first of all, we want to solve this problem by looking at, suppose that we have, this one is too large. Okay, we're going to separate this data, okay, FFT, to a small system, just like what we consider here. Okay, and just like what we are doing in this diagram here. Okay, like in this one, if n is equal to 8, this one is lower, but suppose that if r is equal to 8, this means that you separate the time data to 8 parts, okay? And that's what and for each part, you cannot handle it simultaneously at the same time. So you need to work for each part and then keep it somewhere where the memory, the amount required memory can be handled, which can be your hard disk, your SSD, or your cloud storage. Okay, it becomes the secondary storage, but the main storage, as you see in this Matlab software, is not enough. It's not enough. So I'm gonna illustrate you by example. Okay, we have write a program here we call the big data FFT construction.m. Okay, as you see in the screen here. Okay, and you can see that the first statement, we clear out the memory, so that let all the memory free as much as possible. And this one is n is equal to 741,824. Okay, this is also in the power of 2. You can track it down, try to find it. What is the power of the 2 that lead you to this number? Okay, and we R is that we call this a Radix-r. R is equal to 8. Okay, so when R is equal to 8, it means that we separate the data to 8 pieces. Okay, and NR is n divided by R. We separate to and M is also NR divided by R. You can see that it looks pretty funny. Okay, so in this case, okay, N is equal to NR is n divided by R, and M is equal to NR divided by R. Okay, and this one is the way we're gonna manipulate the data a little bit. And this is a command that in this case we are using a hard disk drive, okay, to help you keep the data on the secondary storage. But at first, okay, this is a file ID name. I create a file, 8 file, okay, the name is F1, F2, F3, F4, up to F8, okay. But actually, if R is equal to 9, you need to add one more statement, file ID 9, if F open F9. Okay, but if you know how to write a program, you can make it a loop program also, but you require the collector operation a little bit, okay. And we start to count the time ticks, okay. And look at the command here, okay. For k is equal 1 to R, if k is equal to more than 1, okay, you open, okay, file 8, all the 8 file ID, okay. And A is mean that, okay, you can see that the attribute of W here is mean that you want to write down the data. F open is when you open a file, and W is that you open it to write something, to put input some of the data. But when you change this attribute of W here in the command of fopen to A, is mean that you want to append it by adding the data from where the last time the data storage end. Okay, why we have to do this? Okay, when K is more than 1, you open this again, and because when K is equal to 1, okay, this is what K is equal to 1 mean. You just open a file. There's no data in the file, so when K is equal to 1, it pass this if condition, go to the next step. But if K is greater than 1, it means now the second round, the third round, the fourth round. Now you need to open this file, okay, for an append, okay, for the append, okay, append. It means that you add the data from the last file, and then you can see that this is what we are doing, okay. FT, okay, is as a metric, okay, that have a M row and R column, okay, and then we generate FT here using this formula, okay. It can be any doesn't have to be this function, okay, but you can generate by any other function for the initial value of time domain. But this is a different time domain that we generate before, because now we do it in a metric form. Why in a metric form? Okay, we have to go back to the way, okay, the Radix-r look like, okay. The Radix-r, okay, for each summation, you can see that this one is xrn, n equal to 0 to n divided by r minus. This one is rn plus 1, rn plus 2r. So it means that each of the file, the first file need to keep x sub n. The second file keep the value of x sub n plus 1. The third file is x sub n plus 2. The fourth file is x sub n plus 3. And so on to the R file is x sub n plus r minus 1, the last file. Okay. So it means that you're gonna skip the data, okay, for every R order, okay. It means that you don't keep the data in sequence, because you want to separate the data. You remember what we did in Excel before, the file Excel, that we need to use the index function to separate the location of the number, so that you can perform the fast Fourier transform in the right manner, okay, according to this formula. The same as this program mean, okay, that actually this is the data, okay, going by for each row, okay, for row number 1, I is row number 1, it go the first R data, okay, the first R data go in the first row, and R plus 1 start the second row, R plus 2, R plus 6 until 2 times R, and reach out until M, okay, M row M, okay, and the last. So the overall data here that they generate at the time over here is only M times R. And what is how much amount of M times R here? You can go back here. M is an R divided by R, okay, and R is for some specific number. So the overall data that they generate here using this command is only the amount of NR, which is N divided by R. Why? Why we only generate N by R? Because as you know that from the file of the file that you get this red signal here you saw on the screen, you cannot generate the whole N at the same time. In this case, around more than 1,000 million, okay, which in this case you're going to face the same problem. Problem in my computer here, I already tested before that you cannot generate the whole data at the same time, because they didn't have enough memory to handle. So you can only generate a partial amount, and then you start spread it into 8 different files. Why 8 different files? Because according to the formula here of Radix-r, you need to keep it, okay, based on the first, suppose the first row, okay, this is you start with n is 0, you get x0, x1, x2, x3, x4 until xr here, xr minus 1, okay, when the same as now you get xr, okay, The next one, when n is equal to xr, xr plus 1, xr plus 2, xr plus 3, until xr plus r minus 1, okay, in the second row. But you cannot generate the whole n at the same time. So in this program, they're going to generate only nr, this one, n. Why nr? Because we have already found that once n divided by r, the size of the problem become manageable and is in the responsive zone, or is a comfort zone for the software that should be able to run and get the result for you. As you know that last time, even a million point, it took less than a minute. Actually, the computer I show you today is even faster than in my house. This one is in my office. Okay, so around, you can see that in this case you get 1,000. Actually, you get 100 million. If you go back and test your computer, you find that under Matlab circumstance, even 100 million, and you have something 8 gigabyte main memory or 16 gigabyte, it's still a manageable size to solve. It means that it responds, it solves the problem. And the problem can be solved maybe within 1 or 2 minutes, or even 100 million points, okay? So the limitation of Matlab is much larger than the limitation that control within the Fourier analysis add in the Excel application. Okay, so now you understand that this program, they're going to generate only n divided by r at a time. And we separate in r column because for each column, okay, for each column, you can see the first r, the next r, the next r, so on. You can see that for each column will be the representation for this one, xrn, xrn plus 1, xrn plus 2, xrn until xrn plus r. So each of these, okay, will be, write it down, okay, save it. We use the command fwrite, okay, write it. Okay, the first column you see here, okay, double here, the attribute double is mean that you're going to keep the result as a double precision. What does double precision mean? It means that actually the computer cannot handle rational number because of the prime number. Okay, if you don't understand what I say, that you go back and then study what is prime number is, and when you represent number by fraction, okay, or rational number, since the largest prime value is unlimited, can go to infinity. So at one point, okay, there exists an integer value that even a computer cannot represent with their how many number of digits they're going to represent the number. So the double is mean that you're going to keep expanding the number of precision to be more accurate. I mean that better approximation. Okay, then you using single. Single is mean that, for example, you use the 8-bit, okay, to represent a number. Double can be 16-bit. But in this case, nowadays the single precision may be 32-bit. Okay, the double is mean that you get 64-bit to represent a number. So that the large number can be increased and more accuracy can be used when they use for in terms of operation under the irrational number representation. Okay, so double is mean that we're going to try to make sure that the approximation can be more accurate. You can see that the first file FD1 is F1, F2, FD, F1. This one, the first column, second column, until the 8th column. Okay, once they finish the 8th column, they go back to the loop, okay, to the second time. K can increase from 1 to 2. You can see that because we cannot generate the whole n data at the same time, so we have to partially generate it, okay, n divided by r. And then the next n divided by r, okay, instead you can see that once we generate partial, we write down and then we close it, close the file. Close the file is mean that now your main memory free, okay, free again, okay, and also so the file now is
has been stored on your secondary storage. And then for the second round, third round, up to the R round, the final round, each time, you're gonna open the file again, this 8 file again, but you didn't open it just to write anymore. Just for the first time you write it down. But with the second round, third round become append. Append is mean that you add the new one, you open it again, so the existing data is still there. So the last address that store the data, the new type data you're gonna install append, okay, and in addition, okay, to the existing data here, okay. So that's what this command do for you, okay. You're gonna keep separating the n to 8 piece of data, okay. For each piece of data, okay, once they generate, okay, they're gonna keep store, okay, keep it in 8 separate file in the secondary storage. And as you know that we cannot use the n data at the same time because n was too large. So with some partial, once you generate the next one, is mean in reality it means that you get the new additional data. You have to reopen the file again and append the data at the last address that you stored during the last last read and write data into a file. Okay, so this is the program that you need to execute first. And the resulting file that you're gonna get it, you're gonna have the file F1, F2, F3, F2 up to F8, okay? And each of them will have the data of n divided by r, okay, installed in here. And each of these files is ready to execute what? Based on the formula of Radix-r, is ready, is in the, once the x has been separated here in time domain, okay, you can apply fast Fourier transform. Okay, for each of these summation, that's r term. Okay, the number of term is r possible term of FFT here, independent of each other. Suppose you have 4 computers, or you have r computer available in front of you. You can separate, use, like you can, as you can see in this file, you can use F1 to execute one computer, F2 execute, F3, F4, F5, F6. Execute into each of these computer. Okay. This one is happen when you have facing a too large problem. Okay. And the second step is that, okay, once you go back to the idea of Radix-r, once you find this, okay, find FFT for each subterm, okay, you need to use this formula, okay, where xk plus n sub k plus capital N times L divided by I is equal to R, M is equal to 0 to R minus 1 W to the M k plus NL divided by R, summation N is equal to 0, N divided by R minus 1 W R to the N k x R N plus N. Actually, this summation on the back here is a summation here, okay, but W that multiply in front of this summation is according to this one is 1. Actually, the first summation, the multiplication by 1, this one multiplied by W to the K, W to the 2K, W to 3K, to W to the R minus 1K. And then once L change, this one is L is equal to 0, first term. But when L is equal to 1, okay, you instead of become 1 WK, W to the 2K, you need to add NL divided by R, okay, to this in front term. Okay, so this will help you that now you can execute to find x bar k. Okay, and this one also x bar. Okay, I forgot x bar over here. I forgot to put the bar sign here. X bar here. Okay, for this second term, this will be x bar, capital X bar. Okay, if we can, because now we have this result. Okay, we can find for each L. Okay. For each L, okay, we can find x bar k, okay, to get the results in the separate format, okay. Separate format is mean that like this, okay. Okay, for for L is equal to 0, you get, if you replace the first term over here, for L is equal to 0, okay, you get x bar k, okay, when 0 to n divided by r minus 1, okay. But when L is equal to 1, okay, when you put on this one, when L is equal to 1, you get x k plus what? When L is equal to 1, k plus n divided by r, you get when k is 0, 1 to t to n, which means that you start with n divided by r and n divided by r plus 1, n divided by r plus 2 until n divided by r, until 2 times n divided by r minus 1. Okay, when you reaching this term when L is equal to 1. Okay, because now you start n divided by r plus 1, n divided by r plus n divided by r and n divided by r plus 1 until to n divided by r 2 times n divided by r minus 1 when L is equal to 1. So you can see this formula work nicely that to decompose the results of x bar k. This one, please remember that I forgot the bar side, okay. X bar here, okay. So this is what we did in the Matlab software. Okay, that now we already separate a big data. Maybe in the case that you already seen is a 2000 million. Okay, we separate into 8 files. Okay, and in this 8 file, okay, you get this. The next step you need to do is you need to based on the formula, you need to find the fast Fourier transform for each the data contained in each file, in F1, F2, F3. In this case, for R is equal to 8. Once you find the what I call you find the fast Fourier transform, you get all the result of this summation. You can use this substitution. The second equation start from L0 to R minus 1 to get all the results of x bar, okay, or the frequency domain. And it becomes each part also, each of them here. Since, okay, k start has a size of only n divided by r, we'll start from 0 to n minus. So for each L, okay, you get the result of x bar here, the frequency domain here, in a manageable size, okay, that you can save into another file, okay. And also if you work on this, okay, you have to make sure that you avoid having to work this by simultaneously download all the data in your memory at the same time, which if you do that, the problem cannot be solved. Okay, so now, okay, we go to the second phase of the program. This is the first phase, the big data FFT construction. The second phase of the program here, okay, is in this case we separate into 8 files, okay. It's a problem that I'll show you here. We're going to have a test big FFT 1, 2, 3, 4, 5, 6, 7, 8. Okay, you can see that this is the 8, 7, 6, 5. Oh, 5 is missing. I should have deleted. Alright. Yeah, I delete the 5. But the program is not easy. It's not that difficult to understand. Okay, we start with test big data FFT 1. Okay, you go back to this data, you can see the original n, okay, is in the power of 2, and r is equal to 8, okay, and nr is here. We don't need mr here because you know. And then we start measuring the time tick, okay, the file idea, the first test big FFT1 is according to the file F1, okay, and then this one is a read. Once you want to read a file that's stored in the main in your secondary storage, you recall the file name, okay, and the amount of data in there is nr, as you know, and double, okay, we remember that we write it down using double precision, so we retrieve it back in the same format. And fread is that read this file, all the data in n divided by r data in the double precision and store in the vector x. Okay, this is you first of all you open the file first, and then once the file open, you need to close it. Okay, so once the file open, close it, so you can open the next file. And this one is only tick tock. This means that I'm going to count the time that
Okay, how much time do I have to just read the data here? And then you can see that the next step here is that I'm going to solve FFT. Because why we are doing this? Because the first part I retrieve the data, I want to find the fast Fourier transform and keep it in WR. Okay, WR. And you know that WR now is become a complex number, as we have seen from last time. That when you execute the FFT command, the result going to be a complex number. So how do we going to store complex number in a file? Okay, we have to separate it into the real part. You can see that this is a command of real part, and this is the imaginary part. Okay, the real of the complex number, in this case, is a vector of WR. Okay, so I say here, okay, again now we get the result of execution, the FFT, so we store back, okay, the result of this FFT, okay, into and keep it, okay, and refer it as a variable we call FWR1, Y1, because now we work on the file F1, okay, and then we write the file, okay, so this is a resulting file of FWR1, okay, we write the file as a file ID, only the real part, okay, the real part of this WR. And the amount of data of WR is, you know, that is NR, is N divided by R. Keep it as a double precision because we all execute the command based from the input data that have a double precision format. And then we close the file. This is the first file. So the second file is that we open again, we call this file, okay, this one we call the file FWR1. This one we call, the name of the file we call FWIM1. Okay, this is imaginary part of one. And then we write down, okay, again, just only the imaginary part. And as a double precision, and then we close the file. Okay. So, again, if you go to test big data FFT2, you just change everything to F2. FWR2, the name of the file that I refer. Okay, but the remaining part is all the same. The one is to just work on file F1. This one F2, F3, F4. And you can see that you can, I forgot to, or something missing about 5, okay, equals 6. But test big data FFT5, you can just change this file to F5, and this one FWR5 and FWIM5, and then run the program. You can see this is a kind of distributing computing, separate, 8 independent or R independent in general. Okay, suppose you work this problem as a group. You have 4 of your friends. Okay, so each of you might take 2 possible R. This guy, okay, I'm working on I 1, 2, 3, 4, 5, 6, 7, 8, separate to 4. It can be run independent to each other. And the result of each run is that once they get the fast Fourier transform of the smaller size problem or manageable size problem, they keep the real value in the file called FWR and the name according to the sequence of the data of the file. And FWIM, okay, is a function. W is mean frequency, okay, and R is that real part. IM is the imaginary part. That's why we call this. And so you can see that this file is at all 6 files. If I execute all these 8 files, okay, I'm going to end up having the result of FWR and FWIM, okay, all 1 to 8 and 1 to 8, okay. And that's what we go back to the Radix-r. It means that I'm doing each of these some smaller summation size, performing fast Fourier transform. Okay, once I perform the fast Fourier transform for this smaller size of summation, okay, I keep it in, and I know that I cannot have all the data in the main memory at the same time. So for each part, once the fast Fourier transform file, okay, I keep it in the secondary storage, create a new file. The real part keep in one file, the imaginary part keep in the other file. So that's the second step. That you can see that all along we have a problem that we didn't have enough memory. So we decompose
okay, the large problem, the big data problem, to a smaller problem, and we can solve the smaller problem. Suppose that we decompose the problem into the small size that sufficiently effectively and efficiently can be solved by using the regular object of FFT under Matlab. And then once you get this result, again, one at a time, you need to keep the result in your secondary storage. You can't just keep occupying your main memory, because if you add more data and using more space, you might be facing the our memory situation, just like what we found before. Okay, so one at a time. Okay, once you get it, and once you get this, now you're ready to use this third formula. This third formula, okay, you just keep taking the result here. The result here you already found. Okay, the lattice, this summation over here. Okay, keep storage is a complex number. Okay, the real part keep in one file, the imaginary part keep in one file, the other file. So if we retrieve them one at a time and perform this formula, you're gonna get the result of the frequency domain of Radix-r here. Okay, so the third program that we are doing here, okay, okay, actually can be done by using this file we call test big FFT processing over here. Okay. No. Since we already do test big data, you can do it by using this file, big data FFT processing 2. Okay, and actually we have a file. Okay, we can do this big data FFT processing down here. Okay. No, we have to talk this file later. Sorry. No, since we already used the test big data FFT here, the next step is to execute this one for each L here, right? L equal to 0 to 1 here. To use this program, okay, this is what you can do. Okay, you using this file we call big data FFT processing 2. Okay, not using big data FFT, big data FFT 2 over here. Okay, so you can see based on this example, n is the same, and r is a n r here, and now we identify something like a b, okay, as a, actually this is w. You can see that w, because w is cos 2 pi divided by n, right? N is overall the overall data. Sine, okay, b is the imaginary part, minus sine, okay, y minus, because if you might recall that your w here is here, e to the minus I 2 pi divided, which is equal to cos 2 pi divided by n minus I times sine 2 pi divided by n, and that's what this part of the program do for you. Okay, we have cos and we have minus sine now here. Okay, and then you get a is a cos over here, and b is minus sine. Now the I have changed. Okay, 2 pi. Okay, don't confuse this I with the I is equal to square root minus 1. This one is become w square. Okay, w square. Okay, when I is equal to 1, this is w. This is when I is equal to 2, this is w square. Okay. Okay, because you can see that should not be here. Okay, it's a little bit tricky, a little bit. We have to go back and
some mistake here in the program because A1 is W, okay, you can see that. And but for I is equal to 2 is become when I is equal to 2 become W also. When I is equal to 3 become W square, W to the 3, W to the 4, W to the 5, and so on until R, okay, when you're reaching this R. And why we are doing this, okay, if you can go back to the formula of FFT extensive here, okay, because you end up you need to have the first one is 1, okay, this one is W is 2, W, you need this multiplication of W, okay, to perform here, and this setup of W here, but I think this program A1 have no problem because we will use actually A1 should be 1 and B1 should be 0, okay, but actually when we define like this it doesn't have any effect because based on the formula we're going to work on only I2 to R, and once they work from 2 to R where you need to use this A and B instead of, that's why the problem, they have no problem, but to make it correctly, this one should be 1 and this one should be 0, okay, because it's if you refer to the formula here, the coefficient that multiply to the first term, okay, and coefficient that multiply to the first term, okay, for all, okay, when K is equal to 0 and L is equal to 0, it's always, you know, the first term is always 1, let's just say, okay, because when K is 0 and L is 0, it's always 1, okay, and that's why we have no problem with this logic, but actually this one A1 and B1 we never use it anyway, but for 2 it's become cos W, and when I is equal to 3 become W square, when I is equal to 4 is a cube of W, and 4 W to the 4, 5, and so on up to W to the R minus 1, okay, and this is W, okay, okay, W vector is you need the complex of A and B, is mean something similar to what we did on the Excel. You might remember that you can combine real part and imaginary part, okay, to represent it as a complex number. This is W is that the A part is a real part, the B part is a complex, and since A and B is a vector, so W become a vector. And this one, even though you go back to big data FFT, the first one is similar to each other, okay? Don't be confused with test big data FFT, okay? We talk about this later, okay? But this one stick with this big data FFT processing too, okay? Okay, first, you can see that this one is J is equal to 1, okay? And this one is a file ID. You work with the real part of the first part, okay? And once you get all the results here, okay, the real part, you retrieve the real part, you open, you read it. You remember that the construction file, you write it. But now the file is already have the data, you read it out. Once you read it out here, you keep it in the storage called WR and WIM. This means that real part and imaginary part, because it's stored in a different separate file. And W and R, okay, you can make a complex vector also by bringing back W and WIM and merge it down to become W, and then you can clear. Okay, actually I should clear both WR and WIM. Okay, actually I should not just clear WIM. I should clear WR also. Okay. Oh, no, I can't clear WR. Sorry, because I just tried to save the memory that I put all WR and WIM and put it back to WR again. I'm using WR, but now WR become complex number. Okay, but so I clear WIM out because I want to make sure that our available memory can be worked. Okay, So for this one, the first part here, okay, I just open the first file, okay, and then get all the results here, okay, of this summation. This is the summation they keep in the first file, okay. And then we go to the loop here for I is equal to R, okay. The loop here, okay, until here, the end here. And this execution of WR here also, okay, is the program that I wrote it for you, okay, to study, okay, to execute this command, okay, to execute this command, okay. We're gonna go to logic a little bit, okay, that you have to know that for each I, okay, when I is equal to 2 or to 3 to 4, you need to go to open the file, the corresponding file that with the I value. For this one, FWR2, and I is equal, for I is equal to T, you go to FWR3 and FWIM3. And you might remember all this keep, sorry, keep the result. This is a F1, F2, F3, F4 until FR. You keep the result of this summation in terms of keep the result of this summation as a small FFT result, okay. So and also they keep it separately, the real part in one file, the imaginary part in the other file. So you need to take it back and put it in. You get FWR in each case to be the original FFT form results, okay, that you find in the file test big FFT for each separate data segment, okay. So for each case, okay, you're gonna get FWR, okay, then retrieve according to the segment of the data. And once you know FWR here, okay, you're gonna use SWR here and add it up cumulatively for each I that change, okay, from I equal to R, okay. As you can see that you get FWR and you get W here, okay, W here, W1, okay, times, okay. You can see that W here is according to, this is the definition of W, okay. You use this W, and then we need to use the power, okay, and time Wj, okay, when j is greater than 1. I'm not gonna go to this, okay. The way what we are doing here for each loop of I, okay, you get this a real part, okay, FWR. Oh no, FWR is a complex number, okay, and we add it up to the previous WRK, okay, WRK from the previous one. Why we are doing this? Because for each I, okay, we are retrieving each FFT unit, okay, and for once you retrieve I, you need to add it up according to this formula, adding up, okay, adding up, okay. And once you add it up, okay, to add up, okay, that resolves this formula, okay. You add for sum of the term. This FWRK change every loop, every time, okay. The loop I change because it's gonna, when I 2, 3, okay, you retrieve different FWR data, okay. With this FWR here, okay, that according to this formula is this, each of this summation, they need to multiply W to the MK plus NL divided by 2, okay. W to the MK NL divided by 2 are related to the parameter we call the J parameter here. In this case, J is equal to 1. J is here, refer to this L here. The same, but J is, in case in this formula, J is L here. Which means that when J is equal to 1, it's referring to L is equal to 0. When L is equal to 0, it means that you're working on this first formula here. Okay? So the result of solving using this program, okay, you end up having result that store in the data called WR is a complex number. Okay, and in this part is the only the results of x bar k here. Okay, for small k is here when L is equal to 0. Okay, so it's gonna keep x bar k only when L is 0. But for x bar k, okay, plus NL divided n divided by r, xk plus n divided by r, the second segment when L is equal to 1, you can applying this software, okay, by changing only this value, the line for it. If you change j is equal to 2, okay, when only change j is equal to 2, the reference file for all of this, you don't need to change anything. It's all just change j, okay. When j is equal to 2, is equivalent when L is equal to 1. And then you get the second segment of x bar results when L is equal to 1. And so on up to j is equal to, in this case, we call with j, so you can solve this problem. J is equal to 2, j is equal to 3, 4, 5. Change it to j is equal to 8. Okay. But you have to make sure that for each j that you change here, okay, you always change over here, okay, the final file here. Because the final file here, we only use FWR, the real part, okay, of WR, okay, the first, I keep in the file number 1, this one file number 1. Make sure that, okay, once your j change from 1 to 2, okay, from 1 to 2, okay, you change this to FWRS2 and FWIMS2, okay, and so on. You can, if you change this to 3, 4, 5 until 8, just change the index of the name at the end here to 3, 3, 4, 5 until 8. You get 8 results of this segment data. Okay, for each segment you get each file, okay, you get the real part and the imaginary part of each segment of x bar according to the L. When L is equal to 0, you get x bar k. Since k is only n divided by r, it's not the whole, right? You can see x bar. When L is equal to 0, okay, when L is equal to 0, once you get the formula, you get x bar k for all k here. When L is equal to 1, another n, so n divided by r number of data you get. And keep it, it will be stored in the separate file, okay. If you change this to 1, to 2, to 3, to 4, until 8, in this case you use segment 8 file. And that's what we are, so I'm going to make a conclusion here, okay. First of all, okay, you go to the big data FFT construction, you solve this problem, okay. They're going to generate F1, F2, F3, F4, F5, F and F8, okay, of 8 different files, okay. Keep the what you call time domain data, okay. But actually you can do this, I showed you last time that the amount of data doesn't have to be power of 2 when you work with on Matlab environment, okay. For example, we can do 2000 million as I showed you, okay. So after you running this, you get 8 different files, F1 to F8, okay. You go back and to run the file of what we call this one, test big FFT1, okay, run it 1, okay. You get the output file FWR1, FWIM1. You test, you solve test big FFT2, okay. Or you can say that you just change this, okay, F1 to F2, okay, and this one become 2 or 2, okay. If you just change F1 to F2, FWR1 to FWR2, FWIM2, okay, and keep it until you go to F8, or if you separate more file, F9, F10, whatever you do, you can do this in parallel or share
working with your friend, you get the file output of FWR1, FWIM1 until FWR8 to FWIM8. According to this problem, since we set up R is equal to 8. Okay. And the third step, okay, you use big data FFT processing tool here. Okay. Start with J is equal to 1. Remember that J is corresponding to the L here in the formula of Radix-r. Okay. And when J is equal to 1, you can run this program immediately. Okay. What they will do here, this is logic that they work on here, on this formula of, okay, Radix-r. Okay. So, oh, sorry. In this case, when J is equal to 1, okay, from line 15 here down until here, you don't need to change anything. Okay, the formula is keep the same here when J is equal to 1. Okay, but you can look at here. The file output that you're gonna store the resulting data of WRK. What does WR mean? WR is this summation of this. Keep for each loop, okay. You keep once you get this summation, you get this summation plus this summation, cumulative summation of all. Until end of the loop, you get the results here, and you have this result only one segment of L, okay, which indicated by this J, okay. When L is equal to 0, in this case L is equal, J is equal to 1, and make sure that when you change J is equal to 2, okay, and rerun this program again, don't forget to create a new file. Make this a 2 also. Because if you make a 1, it will replace the one that you already solved. Okay. Once you finish all this, you get the result. Keep in FWRS1, FWRS2 until FWRS8, and FWIMS1, FWIMS2 until FWIMS8. Okay. And that's illustration that you I just give you an instruction for you to try out on your computer. Okay, and you can see that now in this case you can solve this 1,000 million point problem down here. Okay, so 3 main problem. Okay, we go back to the Google Drive file. All this data is already been here. Okay, you need this big data. First of all, the big data FFT construction. This one, okay, the file is in here. Okay, good. And then you need to have this. Now you can see this one, test big data FFT1. Okay, that you seen in the Matlab code. Okay, and we have 2. You can make a copy of this and put it in your Matlab environment. 3, 4, 5, 6, 7, 8. Run this. Okay. First, you run big data construction first, and then you run this 8 program. Okay. 1, 2, 3, 4, 5, 6, 7, 8. Okay. And then the third part is use this big data. No, not big data processing. Use this big data processing too. Okay. And change the J value from 1, 2, 3, 4, 5. Run it 8 times. Okay. For each J the change, don't forget to add the J value to this index of the file output that you're going to install the data. Okay. If you did this, okay, this is the design instruction for you to run this problem. Okay, you end up be able to solve the case of 1,000 million variable. Okay, which I already did. Okay. But I'm not running it for you, but today we just gave you the idea and the approach how to solve it. Okay, and all the files in here within this drive. Okay, certain, and you can see that what about big data processing 3? This is an additional one, and we use J is equal to 2 for you. Actually, you can do the same as with the test big data FFT that we did. We use the S separate file. This one you can have a separate file by using changing this J is equal to 2, and now at the end you change the file to this one FWRS2, FWIM2. Okay, for 3, 4, 5, 6, 7, 8. Okay, do the same.
Okay, and this one is just one approach. Okay, one approach that we already use the idea, but you have to realize that the approach that we are using is that, first of all, the data is too large to be able to work simultaneously in your main memory at the same time. So you have to decompose it to different segments and try to utilize your memory to work on that segment only one at a time. And once you finish it, you need to clear that memory, okay, or maybe you get all the result back to your file, close the file, and then you open the new file and use the existing memory that you have, okay, that you have previously used in that file with the next file, okay. And that's what the approach we are doing. So we separate the running of the problem to 3 parts, okay. But is there some other way to do it? I think we can further discuss about that. But today, to just I think that just to simplify for you, that the approach that I talk about here, we call the distributed computation. Okay, it means that you have a large system of computation. Okay, that and then you decompose or partition the large problem to a smaller problem. Okay, and each of these problems, some of them you can solve in parallel. In parallel, it means that if you have more than one computer, just like if you go back to to the classic formula of the Radix-r, you can see that if you solve this, you can solve each of these smaller size FFT independent of each other before, but you have to solve it. In this case, you can do it parallel. You don't have to wait for one to get the result. And then the result, you get the file output result, you can put it all together and then continue to work on the last file of big data processing, I think 2, here. That's what we did here. Okay. So there's only one step, is that first you retrieve the problem and prearrange the problem to a different file. Okay, for data segment into each different file, and then you find the FFT for each of these smaller file independent from each other. And the last file is that for each output segment, okay, it keeps retrieving the data from the input from the FFT sub FFT, okay, results, okay, to working on the output segment one at a time also. Okay. And this one, the last part you can see, you can perform in parallel also, because each of these programs independent. One, you can set J is equal to 1, like, and then change the file FWIS1, FWIM1. But when J is equal to 2, okay, okay, I didn't put, if J is equal to 2, J is equal to 3, 4, 5, until 8, if you just change this according this J and then add the number here at the end, the 2, 3, 4, according to the J value, you can also run that parallel to each other. Okay, you don't have to wait one to finish, because the data result will come out for each segment, and then you get the result that install in your secondary storage, and then you share the results or to get maybe online through cloud, whatever. You get all results, keep separately. Again, you cannot put all the results to show in your computer at the same time, because your computer didn't have enough memory to do it. Okay. Next time we come back, and then we gonna talk some further alternative, okay, that actually exists, okay, and maybe you can see in advance that some of the data, like if you look at the file big data FFT processing, okay, this is an integrated approach. Okay, it means that once you use big data construction, okay, you can come in and use this one immediately. You don't need to do just like what we mentioned.
Okay, but there's some pitfall about this approach also. Okay, and then how do you know that you get the right solution? Okay, there also a file to check the solution. We call the test big data FFT here. This big data FFT. You can go and look in advance and how do we test the results here. Okay, and also we have a 5 check solution FFT. Yeah, this is another one that we can check whether we get the solution correctly. Okay, but now you know how to already. Okay, but the next time we discuss about some other alternative approach, and then how we make sure that we get the right result. Okay, and next time should be cover all the topic that you're ready to do the last take-home exam homework. Okay, until then, see you all.